Okay, I got to get back the OneNote, but it's fine. It's recording. There we go. And we're recording. So today we're going to finish. We're going to not finish. No, we're not finished. We're going to continue with section 6.3. So it's section 3, which is 6.3, which is volume. Day 3. Day 1 was volume bound 9 cross sections. Day 2 was disc method. Day 3 is washer method. And what do I mean by a washer? I mean that if we take a disc, suppose I have a disc, right? And it has some radius r. Does that look like our ones where it was delta x? And this was r was a function of x. Remember that one? Do we all agree that that volume, so the cross-sectional area, the area is pi r squared, but the volume for that one disk is pi r squared dx. Agreed? Well, what happens if we subtract out a smaller disk with radius little r, which is a function of x, and that's a delta x? Will we produce that's delta x? Do we produce a lifesaver, a washer? And in our washer, starting from the center, we have an inner radius little r, and we have an outer radius big R. Is it really just two problems in one? Because with the volume of the big one, oh, I didn't finish that. This area, that's area for little r. Little r is equal to pi little r squared. So its volume is equal to pi little r squared delta x, which is dx, right? So if I'm going to do this, am I just going to subtract them? So what do I get? I get volume equals the integral from a to b, whatever that is, right, of pi big R squared dx minus the integral from a to b of pi little r dx. And if they have the same limits of integration and they're both times pi, can I put them together in one integral? I can. You don't have to, but is it so much easier if you'll think in terms of big R squared minus little r squared dx? Because if you put them together and simplify them, what you find is that you eliminate terms or you combine terms, and it makes it easier to integrate and evaluate. Most of the time. Not always, but most of the time. Pretty straightforward? Shall we try one? Actually, before we start, let me just give you the general equation. So this, my examples here I did, this is for if I'm revolving around the x-axis. So this is a revolving around the x-axis. So let's write it all out. So if we are revolving around the x-axis, then my equation is always, so that x-axis revolving around, that tells me it's in terms of x, right? And then what we do is we write, so it's the volume is equal to pi, factor the pi out, integral from a to b of big R of x squared minus little r of x squared dx. You are not subtracting the radii. You got to remember, it's two separate problems. It's not like upper minus lower. It's the upper curve is the outer radius, the lower curve is the inner radius, and those are two separate problems, and you're subtracting out the axis of rotation. But for now, it's 0, right? It's y equals 0, it's the x-axis. X-axis, that means y equals 0. That's my axis of rotation. And before long, is that going to change? Yes, it is. Okay, what if I'm revolving around the y-axis? What is the formula for y-axis? x equals 0, but I mean the axis of rotation is x equals 0, and you're right, it's all in terms of, that was messy, in terms of y. So what do we do? We're going to say volume, oops, I want black, volume equals pi. But now, instead of going from A to B, I'm going from C to D because are these y values. Remember, those are y values. The A and B are x values, the C and D are y values. Is my radius in terms of y now? And my little radius is also in terms of y, dy. Is it that simple? It's that simple. So let's try my favorite functions. Shall we try them in examples? We're going to do two problems. One in terms of x, one in terms of y. You ready? All we're going to do is set them up because y'all can practice integrating later, right? Y'all can integrate now? Mostly? Okay. Let's go to a new page. Can I turn to a new page? Yeah, here we go. Here's example 1 with my favorite functions. Do you need to make sure you can do this no matter where I shift this to, because shift is going to happen to you. What if I give you the region, so I'm talking about the region between, and this is how it's going to be worded, y equals square root of x and y equals x squared is revolved around the x-axis. Find the volume. Pretty straightforward, right? Let's see. So we're going to sketch it first. That's 1. That's 1. Here's 1, 1. Right? What does square root of x look like? What does x squared look like? Did I swag them in? Of course I did. Do you have to make them, I mean, just make them look at get the concavity to work? I don't care. Do we really care? No. Make up your own scale. I don't care. Yes. Michaela would like to come in. All right, looking at this, since we're revolving, so right, show where you're revolving it, right? It's revolving around the x-axis. Oh, I take it it's happy birthday?
Oh, it's not my birthday, it's Mr. K's birthday.
Oh, okay. You just got tagged. Okay. Now, is this the region we are revolving? Does everybody see the region we're revolving? That's the region between. That's how they describe these. So that same region, can I make you find an area? Can I make you fill it with volume by known cross-section? Can I make you revolve one or the other pieces and produce discs? Can I make you revolve that and produce washers? Can I do, with that same region, can I make you do almost every kind of problem? Yes, I can. Be prepared. It's going to come. It's going to happen to you. Here we go. So, we have to label the big R and the little r. So, my big R, the outer radius, so you go from the x-axis. That's our axis of rotation. Go from it. You're going to draw until you get to the outermost. That's the first one. That's the inner. I'm going to keep going until I get to the outer. Is that my big R? It's all the way to the outer surface. Does the square root of x produce that outer surface for this? So is that my big R? I want the radius from the axis of rotation. Do you see it? So we're doing the first part of the problem, which is the outer surface. And we've already done this. Have we already integrated this between 0 and 1 so that we could find a dot, the volume of a dot? Yeah. Okay. So what is that radius? It's equal to what? What's the up for that outer radius I just drew? What's the outer curve? What's the upper curve? And what's the lower curve? The lower curve. This is y equals 0, 0. Okay, tomorrow is that going to be something else? You saw in that demonstration where I shifted it down to y equal -2 and that became my axis of rotation? That's going to change. So put the 0 in there. It's a placeholder. So is my radius just square root of x? That's the outer surface. What about the inner one? Well, here, I'm going to use pink. For the pink, if I go from the axis of rotation up to the first surface I reach, is that the little r? Look where it's shaded. Is there a gap between the bottom of the shaded part, the shaded region we're revolving? Is there a gap between it and the axis of rotation? Do you see that this is a dot with a tornado carved out of it? Do y'all see that yet? You will when I'm finished with you. Okay, is that my little r? What's my little r equal to?
X squared minus 0.
X squared minus 0, thank you. Which is just x squared. So, to make sure you've got this, are you going to draw me a cross-section? You are. And you put your cross-section right here. This is my cross-section right here. Is there an inner part and an outer part? So we go over here. Over here. And so that's my outer radius, right? And is there an inner radius right here? Is that my inner radius? I'm going to change color for that. And we'll pick the pink again. Here's my pink. Actually, I'm going to change colors too. I'm going to make this one the green. Is there my green? There's my green. Is that my outer radius? Outer radius. And is this my inner radius? So if I draw a cross-section for that, that's delta x, yes? That's the disk. Are we going to carve a hole in our disk and produce a washer? Do you see it? I want you to draw this. If you draw that, is it obvious that it's two problems in one? Let's hope so. Do you understand what I'm getting at? You're going to practice this. Just setting them up. Because for most of these problems, the integration is easy. The calculus is easy. What's hard is setting it up properly. But the thing is, if you can't set it up properly, can you get it? Can you get anywhere close to the right answer? Nope. Can you get any credit? Probably not. Because on the AP test, what they're going to say is you're not in the problem because you made something up. And it's not even close to what it's supposed to be. Is it going to be easy to write? Oh, wait, first off, what are my limits of integration? 0 to 1. This is A equals 0 and B equals 1. Go find that, because can I take that region and shift it all over the place? I can do this exact same problem to you on the test, and I will just shift it and disguise it, but it will be the same problem. It's so easy. It's a trick, y'all. Y'all don't remember anything from Algebra 2. No. It's going to be the same volume, but I'm just going to shift it all over the place. Y'all are essentially going to all have the same problem, but you're not going to know it. Evil laugh. All right, can we write the equation now for a volume? Volume is equal to pi, integral from what to what? 0 to 1 of, what was my outer radius? Square root of x squared. What was my inner radius? X squared dx. Do you see that this is two different problems? This is the outer radius. That's the outer volume. This is the inner volume. Two different problems. I just am going to carve out the inner. I'm going to make a dot, and then I'm going to carve out a tornado. By the way, I should draw that for you. What does this look like when I'm done? It looks like, so the outer surface, we're going to do the outer surface, is going to be like this, right? And my inner surface is going to be a tornado. Or a tulip. Yeah, y'all see that? I'm not going to color it in. Why is it? Okay, what it is I took the dot, and I'm going to subtract out a tornado. It's minus this shape. Whoops, sorry. Take that out of that. Right? You've got a dot, and then you're going to carve out a tornado. You see it now? It's weird, huh? Okay, is that going to get it? Is that going to be easy to integrate? Shh, listen. You are integrating x and x to the fourth. Can y'all all integrate x and x to the fourth? Can you subtract? Yeah, you can. You're capable. Can you at least plug in the numbers and leave it alone after you integrate? Yes. Can you use correct notation? Got to work on that. Okay, what about with respect to y? Can I take that same region? Shh. Can I take the same region and revolve it around the y-axis? I can. And so will you be able to before long. Because that way you can pass my test. Yes, but if you don't write the notation correct and your answer is not unsupported, that will be a bald answer and you will get no credit next time because now you've been warned. Just saying. Bald. Okay, this is y equals x squared. This is y equals square root of x. And now I want my cross sections to be perpendicular to the y-axis because I am revolving around the y-axis. Do I have an issue already? Everything's supposed to be in terms of y. Uh-oh, what do I do? Just square it. There's no reciprocal. Oh, square. So this is going to become x equal to, okay, this is square root. Yeah, I know. This is equal to square root of, blah, blah, blah. This is x equals square root of y, and this is x equal to y squared. If you go sideways, does that make sense? Sure it does. Makes lots of sense. Yeah? Yeah? So I'm going to write it right here. This is x equal to y squared. This is x equal to square root of y. I did that backwards. Hang on, I did it backwards. This is x equals square root of y. That's the reason I color-coded it. X equal y squared. There we go, that's better. Okay, inner radius, outer radius. Start from the axis of rotation. Draw till you get to the farthest reach of it. Is that big R? So is our big R equal to, do we have to do right minus left? Remember, it's terms of y. What's the rightmost curve? What's the rightmost curve? Square root of y minus the axis of rotation. What is the axis of rotation if it's the y-axis? This is x equal to 0, right? That's a placeholder because that's going to shift tomorrow, right? Okay, then there's my little r. Need a new color for my little r. Ooh, let's pick little baby blue. Baby blue. Going from the axis of rotation until I get to the first surface. Is that my little r? And what is my little r equal to? Little r with respect to y is equal to what? Yeah, because I go from this surface to the axis of rotation, so it's y squared minus 0. That's just y squared. And this is just equal to square root of y. Can I now, oh wait, have we got our limits of integration? What are our limits of integration?
0 to 1.
Oh, I want this one. Hang on. We want 0 to 1. This is c equals 0, and this is c equals 1, and d equals 1, right? So can we write the integral now? What's our volume equal? Pi. Don't forget the pi. Yeah, really don't forget pi. What am I integrating from and to? 0 and 1. Conveniently. But after I make shift happen, is it going to be 0 and 1? No. Pay attention. What's my outer radius? Square root of y squared minus what's my inner radius? Y squared dy. is this exact same integral as above, only in terms of y. So is it going to be that easy? Yes, it really is. It's that simple.